Hello everyone. Let's continue chapter 8 and finish this discussion. Before we start new topic, let's review this one more time to make sure we all understand it. We said in the hippocampus, the first neuron is going to release glutamic acid. Glutamic acid is going to sit on the AMPA receptor, and as a result, sodium is going to come inside the cell. That sodium is going to depolarize this membrane, and as a result, magnesium is going to get kicked out, and therefore sodium and calcium, they're going to get inside the cell. Remember that glutamic acid also sit on the NMDA receptor. We need both depolarization and the glutamic acid to make sure sodium and calcium is going to come inside the cell. When the calcium comes inside the cell, we said calcium is going to attach to the calmodulin. Calcium calmodulin is going to activate CAMK2, and CAMK2 we said is going to send new receptors inside the vesicle to the surface. As a result, now we're going to respond more to the glutamic acid from the presynaptic neuron. But also, I have to add that CAMK2 is going to attach phosphate to AMPA and NMDA receptor. Attachment of the phosphate to AMPA and NMDA receptor is going to allow them to work harder and bring the sodium or calcium inside the cell even further. So that is going to exaggerate the function even more. We said in the long term, calcium is going to get inside the nucleus, attach to calmodulin inside the nucleus, and then it's going to attach to the protein it's called CREB. I'm sure you remember that we said CREB, when it becomes activated, is a transcription factor. And as a transcription factor, it's going to increase the gene expression, produces a new protein, and this protein adds more spikes or spine to the dendrites that they have more AMPA receptors. And that is basically creating a long-term potentiation, is a change in the structure of the synapses. And this picture shows all the spikes or spines that or dendrite created to create a better synapse with the postsynaptic neuron. We said, however, in the case of long-term depression, the glutamic acid is going to sit on the receptor. Yes, calcium is going to come in, but calcium in this case is going to activate a phosphatase. Specifically, it's called calcineurin. And this phosphatase is going to remove the phosphate from AMPA receptor, and as a result, AMPA receptor is not going to open enough to allow sodium to come in, and the whole system is going to slow down. Now let's add a couple of other things to this one. As you can see in this picture, when the calcium comes inside the cell, calcium also is going to make this cell to produce a new chemical, that this new chemical is a paracrine. And you remember the term paracrine? We said paracrine is a chemical that is released from a cell and affect neighboring cell. This paracrine is going to get released from this postsynaptic neuron, and it's going to come back to the presynaptic neuron, and it's going to make this presynaptic neuron to release even more glutamic acid. In other words, my synapse is going to go to a positive loop. Imagine that you're releasing some glutamic acid. As a result, you bring calcium in, you create paracrine, and paracrine is going to make you to produce more glutamic acid. More glutamic acid is going to bring more calcium in. That is going to make you to produce more paracrine, and this cycle is going to go on and on. For many years, we were looking at this paracrine to see what it is. Many people suggested that must be NO, but the problem was that in the hippocampus, in the pyramidal cells of hippocampus, we don't have enzyme to produce NO. Remember, NO is made by nitric oxide synthase, and the pyramidal cells of the hippocampus, they lack NO synthase. So recently, we know that paracrine probably is a CO, carbon monoxide. I know your book still says it's NO, but if you look at the newer papers, you can see that many authors suggest that this paracrine must be CO but not NO. As we mentioned a few minutes ago, we said long-term potentiation and long-term depression both depends on increasing calcium ion inside the postsynaptic neuron. But the obvious question here would be, how does calcium know I have to take a pathway to create long-term potentiation, or I have to take a pathway to create long-term depression? How does calcium know I have to attach to calcium calmodulin, or I have to activate a phosphatase? Well, it seems like depends on how this calcium increases inside the cell. If the increase of calcium is rapid, it's going to create long-term potentiation. However, if the increase of calcium is small but prolonged, that is going to create long-term depression. That's one of the reasons that they tell you that you have to study in a shorter time and take a break. You cannot study for 8 hours in a row, and also for that reason they tell you to change the subject. When you study chemistry, then next 2 hours study math, or then you study history. So that is going to make sure that you don't create a sustained and prolonged calcium inside the cell, which as a result is going to create long-term depression. That's why prolonged study is not going to increase your understanding, is not going to increase your efficiency, but is going to decrease your understanding of material. As you remember, when we were talking about endocannabinoids, we said endocannabinoids on the memory has a very contradicting results. Some authors, they notice that endocannabinoid is going to create long-term depression. It's going to decrease your memory. You notice that endocannabinoid is going to decrease the release of glutamic acid. They notice that endocannabinoid may remove AMPA receptor from the cell membrane. However, other researchers, they showed that cannabinoid may inhibit the GABA releasing neurons. As a result, it's going to strengthen the release of glutamic acid. So the bottom line is the result of endocannabinoids on the memory is pretty contradicting, so I don't think we have to pay too much attention to this one at this moment. We mentioned that hippocampus is a place that consolidates the memory and also create new memories for us. It should be interesting to you to know that although we don't have any neural stem cells in the brain, but one of the places that you find stem cells will be hippocampus. As a result, it doesn't matter how old you are, as long as you use your brain and as long as you study and try to memorize things, your hippocampus can create new cells and create new synapses. This idea is neurogenesis. Also physical activity and having a supporting environment, having an environment that is not depressing, is joyful, may increase production of new cells or neurogenesis. That's why it would be a great idea if you take your time during the day and do some physical activity, and of course create an environment that is more productive than being depressing or stressful. Moreover, they notice that stress and depression even shrink your hippocampus, and that is being proved by giving antidepressive medications to those people. The hippocampus is going to increase in size, and that can be shown by MRI. Now, let's think about the role of emotion on memory. Sometimes emotion is going to improve your memory, sometimes it's going to weaken your memory. If I tell you, what did you do in your last year Valentine's Day? Probably you can explain everything in detail if that was one of the best Valentine's Day that you had, or if that was one of the worst Valentine's Day you had. If it was a very regular, basic Valentine's Day, probably you're not going to remember all the detail. Why is that? Because when a memory is linked to emotion, then you can remember it very well. That's why in the class I always tell my students, make sure you get yourself excited about the information, because if you make yourself excited and add some emotion to the information, then probably you're going to remember it better. If emotion is added to the memory, amygdala is going to involve in that memory formation. Stress, however, is going to impair our memory consolidation in hippocampus, but also is going to affect prefrontal cortex. Do you remember we said prefrontal cortex is used for working memory, for short-term memory, something that you're going to remember for a few seconds or minute? People are under stress. Even the prefrontal cortex is going to be affected. They cannot even use their working memory. That can be proven by checking the size of hippocampus in patients who suffer from post-traumatic stress disorder. People with post-traumatic stress disorder, they show atrophy of hippocampus. In many cases, people who go through the stress, they may store the information, but they cannot retrieve the information. So if you're studying and you're spending all this time and memorize everything, but when you come to the exam, if you're stressed out Let's say because you're late. Let's say because you had a bad news. You come to the test, you know that you studied the material and you should know it, but the retrieval will be impaired. And the last thing I want to tell you about emotion and memory, remember we have some hormones that deal with stress, like cortisol. We're going to talk about this hormone later. It is suggested that a hormone like cortisol, a stress hormone, is going to affect your hippocampus, and memory formation in hippocampus is going to get impaired. However, this type of hormones increase the emotional memory inside the amygdala. So amygdala is going to store memory that attached to the emotion, but the other type of memory without any emotion that is going to be in the hippocampus would be adversely affected by stress hormone. So that is going to bring us to the prefrontal cortex. If you look at this brain, this is the front of the brain, this is the back of the brain, this is the occipital lobe, this is the frontal lobe. The front of the frontal lobe is called prefrontal cortex. So the whole thing is a frontal cortex, and the front of the frontal lobe is called prefrontal cortex. In psychology, I'm sure they told you that prefrontal cortex is going to deal with reasoning and personality, decision making, and your intellect. Prefrontal cortex is going to tell you that what would be consequences of your actions. Let me give you an example. If you're working and you see that your manager or the director is treating someone unfairly, your emotion tells you that you have to speak up and condemn that behavior. However, your prefrontal cortex is going to tell you if you say something, you may lose your job. So that means prefrontal cortex is going to predict what is going to happen if you speak up. And there's going to be a challenge between these two to come up with the best action. So therefore, we say prefrontal cortex is responsible for intellect, cognition, recall, personality, judgment and reasoning, and conscience. Let me tell you very quickly what cognition is. In psychology, probably you learn that cognition is any cortical activity that results in knowledge, or I would say any mechanism that is used to acquire information. For instance, reasoning, attention, and language, they're all part of the cognition, because all of those is going to help you to acquire some knowledge. Both right hemisphere and left hemisphere, they have prefrontal cortex. And in each hemisphere, your prefrontal cortex is composed of 3 pieces. Here, number 1 shows a part of prefrontal cortex is called orbitofrontal. Number 2 is called lateral prefrontal cortex. And number 3, which you have it also in this hemisphere, is called ventromedial cortex. Also, many papers and researchers suggest that right prefrontal cortex increase the negative feeling in individuals, but the left prefrontal cortex increase positive feeling. So people with depression, probably their left side of prefrontal cortex is not functioning enough, or the right side is functioning too much. There's an imbalance between right and left prefrontal cortex. Also, they noticed that there's a difference between orbitofrontal cortex and lateral prefrontal cortex. It seems like orbitofrontal cortex gives you the ability to consciously experience pleasure and reward. When you damage the orbitofrontal cortex, that is going to create impulsive behavior. It seems like lateral prefrontal cortex is responsible for motivation, sexual desire, and cognition ability or cognitive functions. And that is going to bring us to the last part of this chapter, and that is basal nuclei. So I assume this is the most important part of this lecture, and I want you to pay attention. If this is a brain, and if I cut it in a transfer section that creates upper and lower part, here you can see the section that you cut. So you cut it and you remove the top part, and you can see the section that you cut. You realize that outside this gray area is called gray matter, and the middle part of the brain is whiter color and it's called white matter. I'm sure many of you remember from your biology or anatomy that if an axon is covered by myelin sheet, become white color. So all this white area that you see in this picture must be myelinated axon with myelin sheet. However, if you don't have myelin sheet, that is going to create gray color. just like cell body. Cell body of a neuron doesn't have myelin sheet, that must be gray color. So this area of the gray color, or my cortex of the brain, is composed of all the cell body. So middle part is white color and is all axons, and the cortex is all gray color, means all cell body. However, in the middle of this white matter, you have some gray matter also. And you remember, we said the collection of the cell body is called nucleus. And since these cell bodies are gray color, therefore this gray matter here, all this gray color here, must be nuclei. The biggest nuclei that you all know is thalamus. Thalamus is a collection of the different nuclei. That's why it's a gray color. You remember we talked about insula. We said insula is hidden under the lateral sulcus. And in this picture, this part I'm showing you, this part is your insula. Do you remember this picture? This is your lateral sulcus. And we said if you pull this frontal lobe up and temporal lobe down, then you're going to see the insula. On the other side of the insula, in the medial side of insula, in this picture, this is your insula. This is your lateral sulcus, and this is the insula. In here, this is your lateral sulcus, and this is the insula. In the medial side of the insula, so if that's the insula, in the medial side of insula, you have some gray matter, just like this one that you see here. Or here, this is my insula, this part, or this part. In the medial side of insula, you have a collection of the gray matter. These are nuclei. The first one is just a very thin and stretched line. It's called claustrum. This one is claustrum. The second one, which is this one, is called putamen. The next one is called globus pallidus. Globus pallidus is composed of two pieces. You can see one here and one here. This is called externa, and this is called interna. So let's do it one more time. This is claustrum, this is putamen, this is globus pallidus. And then you have another one, it's called caudate nucleus. This is caudate nucleus. You're going to learn this for anatomy later when you take anatomy. I have to add a couple of more things here. Because putamen and globus pallidus are next to each other, we call them together lentiform nucleus. And also we call putamen and caudate nucleus, these two, together we call it striatum. To make it more complicated, I would say lentiform nucleus, which is composed of globus pallidus and putamen, plus caudate nucleus. These three together is called corpus striatum. Do not mix up corpus striatum with striatum. Striatum is only putamen and caudate nucleus. But corpus striatum is all three: globus pallidus, putamen, and caudate nucleus. Anatomically, your basal ganglia is composed of claustrum, putamen, globus pallidus, and caudate nucleus. However, physiologically, that means as far as the function goes, claustrum is not part of basal nuclei. I'm going to repeat one more time. As far as anatomy goes, structure goes, this is what you see in this picture is basal nuclei. However, physiologically, claustrum has no involvement with the function of the rest of this structure. So physiologically, claustrum is not part of basal nuclei. In physiology, basal nuclei is composed of putamen, globus pallidus, caudate nucleus, and two more nuclei. One is called substantia nigra, and the one is called subthalamic nucleus. Substantia nigra is part of midbrain, and subthalamic nucleus is part of diencephalon. This picture is pretty nice because you can see nicely the insula. This is my claustrum, this is putamen, globus pallidus, externa and interna. As part of basal ganglia, we said we have to consider substantia nigra and subthalamic nucleus as well. So let me tell you the function of basal ganglia. If I want to carry this pen in my hand, I have to make sure my muscles are coordinated, so therefore I can come and grab this one without shaking, without missing the target. So when I have this pen here, I'm going to come and nicely grab this one without any shaking, without missing the target. In other words, I'm not going to come here and miss this one. I'm not going to go and past this target. I'm going to come right on the target and grab it. Who is going to coordinate this muscle to come and get this pen without shaking, without missing the target? Well, basal ganglia is going to do that. That's not the only function of basal ganglia, but one of the functions of basal ganglia is influencing the motor cortex. As a result, I can perform without any trouble. Basal ganglia is going to help planning and execution of the smooth movement. So I'm not going to start shaking. So basal ganglia is a big player on your motor activity, but also basal ganglia is going to contribute to affective and cognitive function. Affective function in psychology is another name for mood. And we already talked about cognitive function. Cognitive function is any type of function that relates to acquiring knowledge. So language and memory and attention and reasoning, all is part of cognitive function. Remember, we said in the case of Parkinson's disease, the basal ganglia is affected. That's why these people cannot move their muscle smoothly. And also they have mask face. They cannot show a normal mood. And also in the later stage, their cognitive function is going to be affected also. So let's see how this one works. Let's say this one is the cortex of your brain. And let's say this is your thalamus. Thalamus loves talking to cortex at all time and stimulate the cortex. So thalamus always stimulate the cortex. But that's not going to work, because if your thalamus keep exciting the cortex, then your muscle is not going to be coordinated in function. So we have to make sure we're going to put leash on the thalamus. Who is going to control the function of the thalamus? The answer is basal ganglia. How? There are two pathways for basal ganglia to control thalamus. One is called a direct pathway, and the other one is called indirect pathway. So let's see what's going to happen to direct pathway, what's going to happen to indirect pathway. Let's start with direct pathway. Part of the basal ganglia, which is called striatum, you remember striatum? It's composed of putamen and caudate nucleus. Is that right? The cortex of the brain is going to send stimulatory neurons to striatum and stimulate the striatum. So this is stimulatory thanks to glutamate. So cortex is going to stimulate striatum. The striatum naturally, normally, is going to send impulse to globus pallidus interna. You remember globus pallidus has two parts, externa and interna. Normally a striatum is going to send neuron to globus pallidus interna, and these neurons are GABAergic neurons. They release GABA, and as you know, GABA is inhibitory. If cortex excites the striatum, so striatum is going to send more of this impulse to GABA interna and block this GABA interna even further. So it's going to block this GABA interna. GABA interna normally is going to block thalamus because of releasing GABA. So now think about it. If cortex excites the striatum is going to release lots of GABA to this one. As a result, GABA is going to block globus pallidus interna. So globus pallidus is not going to release GABA. As a result, your thalamus is not going to be inhibited. So therefore, thalamus is going to keep exciting the cortex. Let's do this one more time. The function of globus pallidus interna is sending GABAergic neuron to thalamus to block thalamus. If you block globus pallidus, then you are blocking sending GABA neuron to the thalamus. And as a result, thalamus has become unleashed, and as a result is going to excite cortex even more. So that is part of your direct pathway. But that's not all. What is the role of substantia nigra here? You remember substantia nigra physiologically is part of basal ganglia. We talked about in the past about nigrostriatal system. Here is my substantia nigra. Substantia nigra is going to send some neuron to GABAergic neurons. It's going to connect this neuron to this neuron. Remember, these neurons are GABAergic, are inhibitory. This neuron that comes from the substantia nigra to the GABA is going to release dopamine. This dopamine has a receptor here, and that is called D1 receptor. When dopamine sits on the D1 receptor, it's going to stimulate this neuron even further. It's going to empower your GABAergic neurons. In other words, substantia nigra is going to increase inhibitory effect of this neuron on globus pallidus interna. After all, because of the pathway, your thalamus becomes more and more unleashed. As a result, excites even more your cortex. So the ultimate result of direct pathway is excitation of the cortex. Now, the good news is, for your class, I'm not going to ask you the detail of direct pathway. You have to know thalamus always excites cortex, and you have to know that substantia nigra is going to excite direct pathway. As a result, the function of the direct pathway will become exaggerated. Also, I'm going to ask you that how does substantia nigra is going to empower this pathway? The answer would be substantia nigra is going to release dopamine that has D1 receptor, and this D1 receptor is excitatory. It's going to excite this pathway. In the case of indirect pathway, I'm not going to go through this detail, but I want you to understand that indirect pathway at the end is going to inhibit thalamus, so therefore is going to inhibit the activity of cortex. So indirect pathway is inhibitory pathway. However, to make sure that thalamus is not going to be completely inhibited, substantia nigra this time is going to send dopaminergic neuron, but instead of using D1, it's going to use another receptor. It's called D2 receptor. D2 receptor is inhibitory receptor. Think about it. If you inhibit an inhibitory pathway, the result of that one would be excitation. So let me repeat one more time. In the case of direct pathway, substantia nigra is going to increase the activity of direct pathway. It's going to excite your cortex more. In the case of indirect pathway by nature is inhibitory. Substantia nigra, when it affects indirect pathway, is going to use D2 receptor, and D2 receptor is inhibitory receptor, so it's going to inhibit indirect pathway, and as a result of inhibition of the inhibitory pathway, that is going to turn to excitation also. So in a sense, substantia nigra is going to increase the activity of direct pathway, and it's going to decrease the activity of indirect pathway. So overall, I would say substantia nigra is going to excite your brain. It's going to make excitation. No wonder people with Parkinson's disease, they are very slow. They walk very slowly because my substantia nigra cannot release dopamine anymore. That means you cannot excite direct pathway and you cannot inhibit indirect pathway. As a result, your cortex is going to slow down. And the last thing I want to add here would be the role of subthalamic nucleus. So what's the function of subthalamic nucleus here? As a general rule, I want you to understand subthalamic nucleus always stimulates substantia nigra. And the very last thing I want to tell you about substantia nigra would be this. Substantia nigra not only has dopaminergic neuron, but also has some cholinergic fibers. The function of the dopaminergic neuron is what I just explained to you. Has D1 receptor and D2 receptors. D1 receptor would be excitatory and D2 receptor would be inhibitory. However, you have to also understand there must be a balance between cholinergic fiber and dopaminergic fiber. When dopaminergic fiber dies, then cholinergic fiber becomes the stronger player for the substantia nigra. And what is the function of cholinergic fiber in the substantia nigra? Cholinergic fiber always stimulates indirect pathway. So since cholinergic fiber always stimulates indirect pathway, one of the strategies that we use to treat people with Parkinson's disease is decreasing the activity of cholinergic fiber. Because by decreasing the activity of cholinergic fiber, then indirect pathway would not be stimulated that much, and also is going to help the people with Parkinson's disease. So don't forget, cholinergic fiber is the fiber that always stimulates indirect pathway. And that is going to bring us to the end of chapter 8.